Hello again everyone, welcome back to ptet.chemistry channel. In this tutorial, I continue this topical MCQs on topic 1, which is just on mole calculations and stoichiometry. In the old type of questions, they do remind you to use data booklet, but when you see this kind of mole calculations, you will know to use the periodic table from the data booklet anyway, right? Okay, so what do we have? We are saying that this ore, the ore ilmenite, give you your TiO2. Of course there's plus something something something. I don't really care. What I care is there is one titanium in there and there is one titanium in there. Okay, so what does that tell us? That tells us the ratio of this is to this is 1:1, because there's no other titanium product, there's no other titanium in the starting material, and you have one titanium here and one titanium in the formula unit, so the ratio is just 1:1, and we are very nice and happy there. Even without the balance equation, we already get the mole ratio. Usually you will see me doing it as a fraction. I mean, I could show you as a fraction. That is just 1:1. When I bring it up, then that is equal to that, you know. So there's no difference to that at all. With me writing this, I'm just writing it all in one go. All right, provided that is 1:1. It's not as simple when it's not 1:1. Yeah, okay. And that's where a lot of students will get it wrong. So we started with 19.0 tons. I'm not sure if you know 1 ton. 1 ton is 10 to the 3 kilogram. So that means it's 10 to the 6 gram. We typically, when we use mass over MR, our mass have to be in gram. But because we started with tons, and our final answer for the TiO2 is in tons, there's no point of converting it into gram to make your life complicated. Instead, what we will do is we will have the mass of FeTiO3 over the MR of FeTiO3, the mass of TiO2 over the MR of TiO2. Typically, you don't see me writing out the formula like that. I'll fill in the value straight away. I just want to highlight to you, if I leave this in tons, therefore this is in tons. Sorry, what I mean is the other way around. If I use the mass of this in tons, then therefore the mass of the TiO2 that I obtained from my calculation will be in tons as well, because the time to the 6 gram will be cancelled out by time 10 to the 6 gram, because everything is in tons. Nice and happy. Don't make your life complicated by converting into it when both of these are in tons. Alright, so use your data booklet, work out the MR of TiO2. So it's 47.9 plus 16.0 times 2. That gives me 79.9. And the MR of FeTiO3 is 55.8 plus titanium is 47.9 plus 16.0 times 3. That gives me 151.7. Started with 19 tons of the FeTiO3. So 19 tons. So I use T to remind myself that it's in tons. This is the mass of the TiO2 in tons over 79.9. So the mass of TiO2 in tons is equal to 19 over 151.7 times 79.9. That gives me 10.0 tons. It shows at 10.01 on my calculator, 10.007, so 10.03 significant figure. Alright, so what is confusing here? There is no balance equation. You just need to think about the balance, the stoichiometric ratio. The second thing that is confusing is, I guess, the value given of mass is in tons, and people might have to convert it to gram if they are very particular about it. But when you think about it, if we leave this in tons, this will be in tons as well. Moving on to the next question. So we have this P4O10 impurity. We react it with calcium oxide. So P4O10 plus calcium oxide, you only get one product, which is the salt, Ca3, PO4 twice. Balance the equation. So you've got 3 calcium here, so you need 3 calcium there. But we have got a problem because we got 4 phosphorus, but we only got 2 phosphorus. So perhaps I should have started with the 4 phosphorus. So I need 2 of these. because I need to have 4 phosphorus, right? And they also specify 1 mole of P4O10, so it's got to be 1 there. You cannot change the number here, all right? So 1 of the P4O10 means P2 times 2 is P4. Then the calcium is 2 times 3, which is 6. So you need 6 of it. Your oxygen is 4 times 2 is 8. 8 times 2 is 16. So oxygen 10, oxygen 6, oxygen 16. Oxygen happy, phosphorus happy, calcium happy. So it's done. So you need 6 mole of calcium oxide. So in this next question, so we want the concentration. We want the concentration of nitrogen atoms. Read carefully, yeah, atoms in this solution. So what do we have? So these are given as mass concentration, so be very careful. These are mass ratio. They are not the same as mole ratio, because the different substance, N, P, and K, they have different atomic mass. This is per 100 gram of the fertilizer. So that is weird. So in that 100 gram of fertilizer, you have 15 gram, which is nitrogen, 30 gram, which is phosphorus, 15 gram, which is potassium. The recommended usage of fertilizer is 14 gram per 5 dm cube of water. So 14 gram fertilizer over 5 dm cube. Okay, and that is the same as how much of it is nitrogen. Out of the 100 gram of fertilizer, nitrogen is the first one, so it's 15 gram is nitrogen. Okay, so 15 gram out of 100 gram of fertilizer. Okay, so there's the proportion, 15 out of 100 gram fertilizer. This is for the whole fertilizer, but you only have 14 gram of fertilizer, so you got to multiply by 14 gram. This is of nitrogen divided by 5 dm cube. This is nitrogen atom, so this is nitrogen atom, not the molecule, but they want the mole. They don't want the gram, they want the mole. So how do you get the mole? The relative atomic mass of nitrogen is 14.0, so we're talking about the atom. So that is 14, so that is in gram. We divide that by 14.0, which is gram per mole. Alright, that is equal to 5 dm cube, because I have only converted the top bit into mole of nitrogen atom. The mole of nitrogen atoms divided by the volume in dm cube, that's going to give you mole per dm cube. Alright, so if we just work it out, so what do I get? I get 0.03 mole per dm cube, and the answer there is option A, 0.03 mole per dm cube. It looks confusing, but it's not too bad after all. So just think about reading through the question, breaking the information down, bookkeeping of the units. Gram is not the same as mole, you want mole, so you need to think about atoms, not the molecule. Okay. Moving on to the next question. So we have limestone. So you will know about limestone when you go to Group 2 Chemistry in topic 9.2. By this stage, I guess I should have told you what is limestone. Alright, so limestone will decompose to give you CO2 and calcium oxide, as you will have learned about decomposition of Group 2 carbonate from your GCSE or O-level chemistry. We are talking about million tons here. So they want the total mass of carbon dioxide produced from these two processes. So first process uses 1000 million tons. Second process uses 200 million tons. So total use for the two processes is equal to 1000 plus 200 million. So there's 1200 million tons. Just like an earlier question when they use tons, here they use million tons. Your final answer for carbon dioxide will be in million tons as well. So realistically speaking, again, we are not going to convert million tons into gram for our mole calculations, but we're just going to be working in million tons and million tons for our masses, and that should be alright. Okay. So we have this and this. So what we're going to do now is we're going to, as you could see, is 1:1 in the mole ratio. I could do the fraction thing again, but as I show you in the earlier question, the mole of this over the mole of this equal to 1/1. So you can just set up this equation to be like this from that relationship. We are working in masses. We want the mass of carbon dioxide. We don't want the calcium oxide. We want the mass of the carbon dioxide, which is also 1:1. So the mass of the carbon dioxide divided by the molar mass of carbon dioxide, which is 12.0 plus 16.0 times 2, that gives me 44.0. So the mass over the MR, the mass over the MR give me the mole of the CO2. The mass of the calcium carbonate total use is 1200. This is in million tons, therefore this one is in million tons. All right, the MR of calcium carbonate, so 40.1 plus 12.0 plus 16.0 times 3, that is equal to 100.1. So mass over MR again give me the mole of calcium carbonate. The mole ratio was just fine earlier, so 1:1. So therefore the mass of CO2 is 1200 over 100.1 times 44.0. I get 527.5 million tons, and if you convert it to the nearest, it's 527.47. so if I convert it to the nearest whole number, that is 527. The closest is 528. That might have to do with this being 100 or 100.1, but this is definitely the closest to whatever we have got, so it's got to be that to be the correct answer. This is the last question of this 5-question series. So this is a combustion analysis kind of question. This is not your typical hydrocarbon combustion because this contains sulfur. So these are gas, 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 and gas. That's very important because they are gas. The mole of a gas is equal to the volume of a gas over the molar volume of gas. Because that is a constant, so we can say the mole of gas is proportional to the volume of gas. And because we're going to be working in volume, and this equation is shown in mole ratio, so we can work out mole ratio as being equivalent as volume ratio of gas. If I have this equation, so CS2, if I just write them down so that I can do and show you what I mean. You have 10 cm³ of carbon disulfide, so the volume used is 10 cm³, and these are in cm³ and cm³, so I'm just going to skip doing it the units. Okay. You have 50 cm³ of oxygen. That is what you use, but the volume reacted, how much reacted, okay? All of this will react because 1 mole reacts with 3 mole. Be very careful here. I talk about mole because this is the equation. 1 mole reacts with 3 mole. But now I talk about volume ratio because the reacting volume ratio is the same as the mole of the gas given the equation. So if you have 10 cm³, it will require 10 times 3 cm³ of oxygen. That would tell you that 30 cm³ reacted. The level of your volume is very important. It's not just volume, it's volume reacted here. Okay, and then volume left, because you already fully reacted all 10 cm³, you got nothing left. You started with 50 cm³, you only reacted 30 cm³, so you're left with 20 cm³. Okay, but then you also have volume formed, because 1 mole of this will form 1 mole of CO2 and 2 mole of SO2. So when you react 10 cm³ of it, then you will form, because of 1:1, you will form 10 cm³ of CO2. 1 mole of CS2 will form 2 mole of SO2. So 10 cm³ of this will give you 10 cm³ of this, and it will give you 20 cm³ of SO2. Bear in mind I said earlier, gas, 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 gas. So we can do the comparison by talking about volume ratio is the same as mole ratio. So the volume of gas after you burn it is going to be, so that is the remaining gases is going to be the 20 cm³ of oxygen unreacted, 10 cm³ of CO2, and 20 cm cube of SO2. Alright, so altogether you have 20 plus 10 plus 20, that is 50. So you get 50 cm cube of gas after you burn it. NaOH is a base, it's an alkali. It will remove acidic gases. I think you learned from O level about SO2 being acidic gases. So this is acidic gas. CO2 is also acidic gas. We can dissolve CO2 in water and it will give you a very weak acid. So we will remove these, and we will remove these. Remove, or we call them neutralize, because these are acidic, neutralized by the NaOH aqueous. So what are you left with then? The stuff that doesn't react with NaOH, the stuff that doesn't get neutralized by NaOH, which is just 20 cm cube. So you're left with 20 cm cube because the CO2 and the SO2 get removed or get neutralized by the NaOH. This is it in this 5-question series. So a bit long because this question involves calculations, and if you enjoyed this tutorial, if you find it helpful, check out all my other topical MCQ playlists as well as other grad playlists on the channel. Do subscribe and share the channel with friends and class group chat and your big wide social network of friends, and hopefully it will benefit more people. And thank you for watching. See you in the next video.